work and the application of the theorem to formulate the boundary value problem. Okay. Last time I showed you that the principal virtual work allow you to replace the classical equilibrium equation by the virtual work equation, right? So that allow you to get the alternative formulation of the problem, okay? And the principal virtual work is the basis in the development of the formulation for finite element approach. If you plan to take finite element class next semester, you will see that principle again, okay? Today, I will talk about the principle of complementary virtual work. Okay, I think you guys are familiar with this principle, right? So at least in the context of structural analysis, okay? You saw this principle when you try to calculate the displacement, okay, or movement or diffraction, rotation of the structure, right? Okay, I think you learned this with Professor Swakeshai before, right? Okay, and this principle can be used to prove several results in flexibility approach. Okay, so I will try to show you the background of the theorem here and show you how to prove it in the context that it's more general than the one that you saw in structural analysis class. Okay. The statement of the principle is very simple here. Okay. So let's consider a body. Let's say that we have a body omega here. Okay. And let's say that the body is subjected to the deformation. Okay. And displacement and deformation. Okay. Let's say that on the surface SU, we know the displacement U0. Okay. So the principle just simply states that the deformation is compatible. The deformation that I talk about here in the context of solid mechanics, we talk about strain. Okay, we use strain to measure the deformation of the body. So the theorem just said that the deformation is compatible if and only if the external complementary virtual work and the internal complementary virtual work are identical for all admissible virtual stresses. Okay, it's very simple statement, but it's very useful. Okay, we can use this principle to replace the classical condition on the compatibility of the deformation and displacement by the complementary virtual work equation. Yeah. Before I prove the theorem here, let me remind you about some of the technical terms that I am not sure that you are familiar with all the terms that I put in the statement here or not. Okay, but if you learn about this theorem and apply it before in the analysis of deformation or displacement of the structure, you should be familiar with all the terms. Okay, the first one, what do we mean by the deformation is compatible? Can anyone here tell me what if I say that the deformation is compatible? What does it mean? It simply say that the strain field epsilon is compatible. Okay, the deformation is compatible. That implies that the strain field epsilon is compatible. You know what do I mean? What the the meaning of compatible strain field, right? So I mentioned about this before, okay, and you learned this condition with Dr. Tirapong in the first part, right? Okay, so the deformation is compatible, that equivalent to saying that the strain field epsilon is compatible and consistent with the prescribed displacement U0 on the surface SU. Don't forget that on that surface, the displacement at every point is known equal to U0. So if I say that the deformation is compatible, besides epsilon is compatible, you also require that strain there have to be compatible, have to be consistent with the prescribed displacement on the surface SU as well. Okay, that is the definition of the deformation is compatible. Okay, or if you express this mathematically, what do I mean by epsilon is compatible? It means that it satisfies compatibility conditions, right? So last time I showed you the compatibility of strain is simply ensured by this condition, right? So double curl of epsilon have to be 0. Okay, so we have 6 independent equation here. If you don't like the expression in this form, you can write it down in the typical way that you saw in Ajahn Tirapong part, okay? Or I told you that, okay, if you write down in that form, you have 81 equations, only 6 of them are independent. So here, if you would like to single out all 6 independent equations, you can write it down in terms of double curves of strain, okay, equal to 0. Okay, so strain is compatible implies that this equation have to be satisfied. Okay, and also strain is consistent with the prescribed displacement U0. What does it mean? One strain is compatible, so you can get the displacement field, right? So this displacement field exists, and that displacement field obtained from the strain field have to satisfy that condition. So that's what I mean by consistent with the prescribed displacement. Okay, so the deformation is compatible simply means that this equation are satisfied for every point x inside, and that condition is satisfied at every point on the surface SU. Okay. The virtual stress delta sigma. Okay, I use the symbol delta sigma here to and I use this symbol to stand for the virtual stress. What do I mean by virtual stress? So basically, virtual stress is the fictitious stress resulting from the thought process. It's not the real quantity. It's stress field that I imagine, okay, in the thought process. Okay, so the admissible virtual stress, I just simply supply the admissibility condition to the virtual stress. Okay, so admissible, I need virtual stress that satisfies some condition. For example, it have to be smooth enough. Okay, smooth in the sense that you can take derivative of stress field, because you need to, if you want to verify equilibrium condition of stress, you need to take the gradient, the divergence of stress field, right? So you simply involve the derivative of stress field. So stress have to be smooth enough in order to perform the differentiation. So I require that the virtual stress that I imagine in the thought process is smooth enough. Okay, and also stress, the virtual stress have to generate zero traction on the surface ST. Okay, so virtual stress is admissible if you look at point on the surface ST. Okay, on that surface, every point on that surface, stress have to generate traction equal to zero. Okay, or you can say that when you take delta sigma ij multiplied by nj at point on the surface st, you have to get zero. Okay, so virtual stress is called admissible virtual stress if it's smooth enough and you can check equilibrium equation or equilibrium condition on that virtual field, and also satisfy the zero traction or traction-free condition on the surface ST. If these two conditions are satisfied, now we can say that that virtual stress is admissible. Okay. The virtual body force. How can I define the virtual body force? I use the symbol delta P. So I add the symbol delta in front of P to emphasize that this quantity is not real. Okay, it's virtual. It's the quantity that induced in my imagination. Okay, in the thought process. Okay, so basically, the virtual body force is the body force that is in equilibrium with the virtual stress. So you can think about that. Okay, you try to imagine the fictitious stress in the thought process. That fictitious stress have to be equilibrium with some of the body force, right? Okay, that body force we call the virtual body force field. Okay, or you can say that delta B is simply the field that generated by the virtual stress through this equation. Okay, delta Bi is simply minus delta sigma ij comma j. How can I come up with this condition or this quantities? Basically, I told you that okay, the virtual stress have to be admissible. So the virtual stress have to satisfy equilibrium equation. So basically, delta sigma ij comma j. Okay, we have delta sigma ij comma j, right? Plus delta Bi equal to zero. So that equation have to be satisfied, right? Because admissible virtual stress have to satisfy equilibrium equation. So now based on this equation, if I give you delta sigma ij or I imagine delta sigma ij, so now I can generate this one easily by just simply move this to the right hand side. So now I get delta Bi equal to the negative of delta sigma ij comma j. Okay, so whenever you introduce virtual stress in the thought process, now you can compute virtual body force field easily using this formula. Okay. How about virtual traction? Once I introduce delta sigma. Okay. Let's just simply focus on the admissible virtual stress. Okay. The virtual stress that is admissible have to satisfy the condition on the surface ST, right? So we need the traction on that surface equal to zero. But how about the traction that generated here? It may not be equal to zero. Okay, so the virtual traction that generated by a virtual stress can be calculated easily using the Cauchy formula, right? Okay, so basically delta Ti is simply delta sigma ij multiplied by Nj. Okay, that what I call the virtual traction. But if virtual stress is admissible, So delta Ti here is 0 on that surface, right? Okay, so that is the condition that we require for virtual stress to be admissible. But on that surface, at every point on the surface SU, delta Ti can be non-zero. Okay. Now, let's move to the external complementary virtual work. What is this quantity? So I defined the external virtual work before, if you remember, right? So the external virtual work is simply the virtual work due to external force, or the work done due to the external force. Where what? The virtual displacement. This is the conjugate pair. I can think in that way. Okay, so if you take a look at the graph here, if we have the graph between P and U, let's say that P here is the external force, and U here is what? Displacement. Okay. Sorry. So let's say that we have the relationship between P and U like this. If you try to compute the work done, if you remember, the area under the curve here, we define this the work done, the external work done, like, right? Right. Okay. So now we can also define the complementary quantity that we call the complementary work done. We define that as the area under the curve as well with respect to the vertical axis here. So this area we call the complementary work done. Okay, so now if we understand the way that we define the work done and the complementary work done, we use the same idea here to define the external complementary virtual work. Okay, because when we take a look at the virtual process, the real quantities are fixed because we stop the real process, but we introduce the process in the imagination. So now, if we talk about the external virtual work, as I mentioned before in the principal virtual work, so we fixed the force, okay, the real force, but we introduce the virtual displacement. So in that case, we can compute the external virtual work easily by simply by multiply the real force, which is constant during the process, with what? The virtual displacement. Now you can get the external virtual work. But here, we can do using the concept, the same concept that we define for the complementary work done. So now the external complementary virtual work can be obtained by simply take what? The real displacement that fixed in the thought process. We imagine that, okay, we have the virtual stress generated inside the body. And that virtual stress will generate the virtual force, like the virtual body force and the virtual traction. And the virtual force that I talk about there, we can think about that external force, but it's not a real one. It occurs in the thought process. So the complementary work done due to the real displacement through the external virtual forces that generate the external complementary virtual work. Okay, so if we understand the concept of the complementary work done, I think we can define the external complementary virtual work easily. So basically, the complementary work done here, we look at the complementary work done of the real displacement, where the virtual body force and the virtual traction, okay, resulting from the virtual stress. Okay, that is the definition. How about the internal complementary virtual work? We define the complementary internal complementary virtual work similar in a similar way. If you remember in structural analysis class, if you have stress here and you have strain here, okay, you have the relationship between the two like this. Can you tell me the meaning of the area and the curve here? What is that? The area under the curve is what?
Energy, sir.
Can you say again?
Strain energy.
Okay, we define that quantity, the strain energy density. Or you can think about the internal work done per unit volume of the material, right? So this is simply the internal energy, right? Or the internal work done due to stress. Okay. Or we can say we can call this the strain energy density, right? Now if we look at the area here, that is a complementary quantity. Okay, so what we define this quantity as the complementary part of that one, and that is simply the internal complementary work done due to stress per unit volume. Okay, if you take the integral of that area over the whole body, now you can say that that is the internal complementary work done. Okay, and that part is the internal work done. Okay, per unit volume. If you perform the integral of the area here over the whole body, now you get the internal work done of the system. Okay, I will use the same way to define the internal complementary virtual work. The internal complementary virtual work is simply the complementary part of the internal virtual work. Okay, you know how to define the internal virtual work in principle virtual work that I mentioned last time, right? You know how to define that quantity, but the one that we have here is simply the complementary part. Okay, you can look at the two areas here. One is the complementary part of the other. Okay, so now I can give the definition of the internal complementary virtual work. It's simply what? It's simply the complementary work done of strain, where the virtual stress in the thought process. Okay, is that clear to you? So when we talk about the internal virtual work, we talk about the work done of stress, where the virtual strain. But when we talk about the complementary part, we talk about the internal complementary virtual work, we talk about the complementary work done. So we add the wording complementary here. So we talk about the area on the other part, right? We have the area with respect to x-axis. We also have the area with respect to the vertical axis as well. So the complementary part here is simply the work done, okay? Work done with respect to different quantities, with respect to different axis, right? If you look in that way. So basically the internal complementary virtual work is a complementary part of the work done due to stress. Okay, so then this can be defined in terms of the complementary work done of strain. Strain that I talk about here is the real strain. Okay, and the stress that generates this complementary work done is the virtual stress induced in the thought process. Okay. Now I will give you the explicit expression of the external complementary virtual work and the internal complementary virtual work. It may be clearer. Okay, if you see the expression. Okay, let's say that okay, I introduce the admissible virtual stress delta sigma to the body here. Before I did that, I freeze the system. Okay, I freeze the real process. I stop the time there, and then I introduce admissible virtual stress in the thought process. Okay, so delta sigma here is not real. It's the fictitious quantity. Okay, and also satisfy the admissible condition. So delta sigma here have to be in equilibrium. Okay, sorry, delta sigma here have to be smooth enough that you can take derivative of that quantities in the equilibrium equation. And also delta sigma here generates zero traction on the surface ST. That's what I mean by admissible condition. Okay, let's say that okay, we introduce the admissible virtual stress in the thought process. So now I can generate virtual body force, right? From equilibrium equation. So now I can generate delta BI from delta sigma ij. Okay, I take derivative of delta sigma ij, or take the divergence of delta sigma. Okay, so you can see that if the virtual stress is admissible, so I don't need to worry about the differentiation here, right? We can compute the derivative here because delta sigma is smooth enough. So now I can generate the virtual body force. Also, I can generate the virtual traction. I simply take the virtual stress multiplied by n, our unit normal vector to the surface. And we know that delta t here is 0 on the surface ST because virtual stress is admissible, but it can be non-zero for point on the surface SU. Okay. Whenever I introduce the admissible virtual stress, I can always compute the corresponding virtual body force and the virtual traction on the battery. Okay, so now I can compute the external complementary virtual work, as I gave you the definition before. So the external complementary virtual work is simply the complementary work done due to the displacement, due to the actual or the real displacement through the virtual external forces, the two here. So based on that definition, and we know that when we introduce the thought process, we freeze the real process. So the displacement is constant. Okay, it's constant during the thought process. So now you can compute the complementary work done easily. Okay, we know that okay, the actual displacement remains fixed during the process. So now we can compute the complementary work done due to the displacement inside, okay, inside the body. So just simply take the dot product between the real displacement and the virtual body force. You can think about this is the work done as well. The work done due to the virtual force delta B through the real displacement U. You can think in that way. So if you try to compute complementary work done, you can think about that is the work done due to the virtual force. Okay, if I look at the term in the sense that it's a complementary work done, I would think about that is the complementary work done due to the real displacement. But you can think of in the opposite way. Okay, the complementary, the external complementary virtual work is simply the external virtual work due to the virtual force. Okay, it's the same. Okay, I can also look at the complementary work done due to the displacement on the surface SU as well, because on that surface delta T can be non-zero, right? Delta T that generated by the virtual stress. Okay, so that's what I call the virtual traction. But the virtual traction on the surface ST is 0. So the complementary work done due to the displacement on that surface is 0 too. Okay, but on that part, we know that the displacement is U0, and U0 here can be non-zero. Okay, so now I can add the work done due to the virtual traction, okay, on the boundary as well. Okay, so because I told you that, okay, the traction on that side is 0. Okay, now I can simply reduce the second term on the right hand side here to that one. Okay, because the displacement on that part we know, right? That is simply U0. Okay, this is the final expression for the external complementary virtual work. Do you have any question about this expression? If you try to go back, refer back to the equation that you used in the analysis of the structure. You used this equation before, but not in the context of the body force or the traction. You talk about the force that apply to the structure, right? So if you remember, when you try to apply the complementary virtual work in the analysis of the structure, you have to introduce the virtual force system, right? The virtual force system that I talk about is simply delta B and delta T here. And now you try to compute this quantity. You try to, okay, get the real displacement, right? So in that analysis, you go back and try to connect to what you have learned before, okay? It will be clearer, okay? The final expression that I have here can also be expressed in the initial form. Okay, I can replace the dot product here by the expression like this. Okay, if you like, okay, you can express in this way as well. They are the same. Okay. Also, I can give you the explicit expression for the internal complementary virtual work. Again, based on the definition that I gave you before. So the internal complementary virtual work is simply the complementary work done due to what? Strain, right? Simply the complementary, the internal complementary work done. Okay, so let's say again that, okay, I introduce the virtual stress that is admissible. Okay, so now I can compute the internal complementary virtual work based on the formula here. Okay, I just simply compute the complementary work done due to strain, the real strain that generated in the body. But the real strain here, or the actual strain here, remains fixed during the thought process, right? Because I stopped the real process. So then epsilon doesn't change in the thought process. I can say that epsilon is fixed, okay, during the process, during the thought process. The real process is frozen. Okay, so now I generate the virtual stress delta sigma in the imagination, in the thought process. So you can introduce delta sigma without the chain of epsilon, the real one. So now when you try to compute the complementary work done, that is very simple because epsilon here doesn't change while you introduce delta sigma. So now the complementary work done is simply the dot product between the two, right? And then you take the integral over the volume because epsilon dot with delta sigma is simply the complementary work done per unit volume. Okay, so now if you want to get the complementary virtual work, complementary work done in the thought process, you just simply compute this quantity. Okay, and this is the initial form of the expression. It's very straightforward, right? Whenever you know strain, whenever you know strain field, and you introduce the admissible virtual stress delta sigma, you can always compute internal complementary virtual work from this expression. Okay. Do you have any question about anything here? No? Okay. Now, if you look at the statement of the principle here, if you look at this part, we say that okay, the external complementary virtual work and the internal complementary virtual work are identical for all admissible virtual stresses. Okay, this can be replaced by, or we can set up this condition, and we call that the complementary virtual work equation. And that equation implies what? The internal complementary virtual work is equal to the external complementary virtual work. Okay, so that's what we call the complementary virtual work equation. Okay, or more explicitly, so I replace the expression that I showed you before. Okay, so I replace the expression for the internal complementary virtual work here and the external complementary virtual work there. Okay, so the two quantity here have to be the same. Okay, so that what we call the complementary virtual work equation. Okay, or if you like to express in the initial form, that is the one that we get. Okay, now I can write down the statement of the principle in different way. Okay, I can say that the principle of complementary virtual work is simply the equivalence between the two statements here. So the deformation is compatible and the complementary virtual work equation is satisfied for all admissible virtual stress delta sigma. Okay, so I just simply replace that statement by that one. Okay, so that statement is simply the complementary virtual work equation is satisfied for every choice of the virtual stresses. Okay, or if you like to express this principle in mathematical style, you can also write down like this. Okay, so I can replace the deformation is compatible by these two conditions. Okay, if you remember, so that one can be replaced by that one, and the statement here I can write down like this. Okay, so this is the theorem. Okay, this is the principle complementary virtual work. So these two conditions are equivalent to that equation that satisfies for every choice of delta sigma. Okay, if you like to express the theorem in a mathematical style, you can get principle like this. But if you don't like that, you can go back to the original statement like this. They are the same. Okay. Now I will prove this theorem for you. How can we prove this? Because the theorem here just simply implies the equivalence between the two here. So if we plan to prove this, now we have to show the implication in both directions, right? Similar to the one that I proved before. Okay, the principle of virtual work. So when I prove that principle, I have to prove the implication in two directions, right? We will do exactly in the same way here. Okay, let's say that the statement here is P and the statement here is Q. So we try to prove P if and only if Q, or P is equivalent to Q. How can we prove this? Again, you learn this from logic class, right? So to prove this, we have to prove the implication, the forward implication and the backward implication. Right? Okay, the first thing I will prove P, if P or P imply Q. Okay, the forward implication. How can I prove this? So to prove this, I will assume P, and I will show you that, okay, Q is also true. Okay, if you assume that P is true, and you can prove that Q is also true. So now you say that you complete the proof for the first implication here. Okay, so now let's start by assuming P. Assume that, okay, the deformation of the body is compatible. Okay, I assume the condition P. Now I have to prove that Q is true. Okay, or prove that the complementary virtual work equation is satisfied for every choice of admissible virtual stress field. Okay, how can we prove that? Now we can start from the assumption that we made here. Okay, we assume that the deformation is compatible. What does it mean? What does it mean? What does it mean? I told you about the definition of deformation is compatible, right? So now we know that if the deformation is compatible, what does it mean? Strain satisfy compatibility conditions. That imply what? The displacement U exists, right? Is that right? The displacement U exists. You don't need to worry about the existence of the displacement field because you know that the deformation is compatible. So compatibility conditions are satisfied. So now the displacement U exists. And also satisfy that equation, right? Is that right? Okay. If deformation is compatible, strain satisfy compatibility condition. It's implied that this equation 1 here can be integrated to get the displacement field. This equation is integrable. I don't need to worry about the existence of the displacement. I can always get the displacement from that equation. Okay, and also the displacement have to satisfy that condition as well, right? So that is the definition of the deformation is compatible. Okay. Okay, so the displacement that I got from 1 have to satisfy the condition on the surface SU. Okay, this is the starting point. This is what I assume. Okay, I assume that the deformation of the body is compatible. So I have this condition. Okay, now I will start from what I have here. Okay, to prove that Q is also true. Okay, now let introduce any admissible virtual stress in the thought process. Okay, I try to imagine that, okay, I have any admissible virtual stress. Okay, I use the word any here, imply that delta sigma can be anything. It can be any second order tensor that admissible. Okay, only thing that we have here for the restriction for the delta sigma here is simply have to be admissible. It have to be smooth enough that we can perform differentiation of that tensor. And also it have to satisfy the zero traction on that boundary. The rest is arbitrary. Okay. So let's imagine that we have delta sigma in the thought process. Delta sigma here is smooth and delta sigma I, j, and j equal to 0 on the surface ST. Now I can form the inner product between strain here and virtual stress here. Or I can say that I take the dot product or inner product to this equation. Okay, take I multiply this one to that equation. I can say in a simple way like that. Okay, take the inner product between this equation and delta sigma, and then I perform the integration over the volume here, over the whole body. What will I get? I will get something like this. Okay, I didn't do anything except that, okay, I perform the inner product. Okay, I have epsilon ij here, right? I multiply by delta sigma ij. So this multiplication imply the summation as well, right? Because we have two dummy indices here. So the summation on I and j range from 1 to 3, right? So this imply the product and the linear combinations. Okay, I take the inner product between epsilon ij and delta sigma ij like this. And on the right hand side, I do exactly in the same way. And then I perform the integration over the volume. So this equation is still true. And it's true for any choice of delta sigma that admissible, right? Okay. And then I can use the symmetry of virtual stress, right? Because virtual stress is a stress field. Except that, okay, it's not real, but it's still a stress field. So it have to be symmetric, right? So it have to be symmetric. The virtual stress here is symmetric. If you remember, delta sigma is symmetric. Term on the right hand side can be reduced, right? To what? I used to show that to you before when we try to prove what? The principal virtual work, right? So I can now reduce term on the right hand side to the one here. Is that clear to you? I showed you before in the proof last time, right? So whenever we have the second order tensor that's symmetric, you perform that dot product with the other tensor. The skew symmetric part will not contribute to the product there. So now you can see that we can always add the skew symmetric part. Okay, because this is a symmetric part, I can add the skew symmetric part without changing anything. So now this can be reduced to the one here. Okay, is that clear? Okay, now I can change from 3 to 4 by simply using the symmetry of the virtual stress delta sigma. Okay, and then what? I can use the product rule of differentiation. I know that, okay, if we take the differentiation of the product between ui and delta sigma ij, so now I can use the product rule of differentiation. I get these two terms, right? Okay, so the first term here, you just simply take differentiation of the second function here, and this you take derivative of the first function, okay, and then you combine them, right? This is the product rule. And if you take a look at this one, this is similar to the term on the right hand side of equation 4, okay? This is term on the right hand side of equation 4. So now I can write down that in term of the other two here, right? So basically I will get this. So that term is simply that one subtract by that one. And now I can replace that term into equation 4 that I got before, right? So once I did that, I plug in equation 5 into equation 4. Now I get this equation. Okay, so 4 becomes 6 here. So basically, I just simply modify the term on the right hand side of equation 4 by using the result from equation 5. Okay, so now if you take a look at the term that you got here, take a look at that one. What is that term? What is that quantity? What is that? You have ui delta sigma ij, the whole thing here. You put the comma j here. If you take a look, the product inside here, that is simply a vector with the free index I. So I can say that this one is simply a vector. I can call that, for example, vi. Okay, we have only one free index I. So this one, let's say that I call it vi. Oh, sorry, vj. Sorry, the free index is j, not I. Okay, so the index I disappear because dummy index, right? So now I can say that this is simply a vector with the component j. So if you write down in that way, so what you have here, the integrand that you have here is simply vj comma j, right? Right? So what is vj comma j? That is the divergence of a vector, right? So this one is simply the divergence of a vector. Now you can go back to the divergence theorem that you learned from Ajahn Thirapong, right? So now I have the integrand here is the divergence of a vector. So now I can change, or I can switch to the volume integral here to the surface integral or to the boundary integral. Okay, I apply divergence theorem to the first term here. Okay, now I get this. Okay, I just simply replace the volume integral here by the boundary integral. Okay, this is simply Vj Nj. Okay, so you take the integral over the volume of the divergence of a function, divergence of a vector. So now you replace that by the integral on the boundary of that vector dot with our unit normal vector, which is Nj here, right? So this is Vj that I talk about. Okay, so I didn't do anything else except that apply the divergence theorem to the first term. Okay, is that clear to you?
Yeah, Ajahn.
Okay. Now I can look at the term that I got on the right hand side. What can we do with the two terms here? If you look at that term, can anyone tell me what is that? Delta sigma ij comma j. Is that equal to what? Think about the virtual body force. Is that delta minus delta bj minus delta bi? Is that right? Because delta sigma is admissible. So the divergence of that delta sigma give you the negative of the virtual body force. Go back and take a look at the definition of the virtual body force. Okay, and also if you take a look at that term, that is simply delta t, right? The virtual traction. Is that right? Because you take delta sigma and multiply by n, which is our unit normal vector, that generates traction. And that traction we call virtual traction. And that one, we take the divergence of delta sigma that give you the negative of virtual body force. Because we know that delta sigma here is admissible, so the virtual traction that generated on the boundary is zero on that part. Okay, so delta t is zero on that part. Okay. Based on this information, now I can get what? I use this like I just explained. Delta bi is simply the negative of delta sigma ij comma j, right? And delta ti equal to this. And we know that delta ti or delta sigma ij nj is zero on the surface st, like I just explained to you. Okay, based on all this condition. So the equation that I got before reduced to this one. I didn't do anything with the first term on the left hand side. I just simply modify the two term on the right hand side. Okay, the first term on the right hand side. Okay, I just simply replace delta sigma ij nj with delta ti and use the fact that delta sigma ij nj is zero on the surface st. So now you can see that the integral over the boundary reduced to the integral over su. I get rid of the integral over st because delta sigma ij nj is zero there. Okay. And I also replace delta sigma I, J, and J by virtual traction. Okay, you can see that. For the second term on the right-hand side, I use this relationship. Now I can replace delta sigma I, J, comma J by negative delta BI. And finally, I get this second term. Okay. So this is what I got. And this is what we call the complementary virtual work equation, right? So if you take a look at the term on the left-hand side, this is what? This simply the internal complementary virtual work. And that is simply the external complementary virtual work. Okay? And you know that this equation is satisfied for any choice of admissible virtual stress field, because at the beginning when I introduce delta sigma, I don't have any restriction on the choice here, except that they have to be admissible. So I can say that this equation is satisfied for any choice of admissible virtual stress field. Okay. Now I end the proof because I got P already, right? Now I got Q already. I start by assuming P. And then finally, I got Q. I got that equation. I know that this equation have to be satisfied for every choice of admissible virtual stress field. Okay, that end the proof for the first implication or the forward implication here. Okay. Okay. Just a minute. Okay, I will be back. So maybe if you have any question, you can think about the question. I'll be back in 1 minute. Okay, I will show you the proof in the second direction. Okay, just a second. Okay. Do you have any question about anything about the proof that I just showed you? Any question? No? Okay. So now let's move on. Look at the proof of the implication in the backward direction. So now we will assume Q and try to prove P. Okay. The proof of this implication is more difficult. Okay. It requires the knowledge in vector calculus. I assume that okay, you guys learned that from your undergraduate level before. Okay. We start by assuming Q. So what does it mean? So let's say that okay, the complementary virtual work equation is satisfied for every choice of admissible virtual stress field. So this is what I call assume Q. Okay, we know that Q is true. We know that the complementary virtual work is satisfied for all admissible virtual stress. Okay, this is starting point. How can we use this condition to prove that the deformation is compatible? Okay, so this is what we have. Okay, that's what we have from Q, right? So this is the virtual, the complementary virtual work equation, and this one is satisfied for every choice of admissible virtual stress. Okay. Now, we know that delta sigma is admissible. Okay, so we can generate delta B from delta sigma like that because delta sigma is admissible, so we don't need to worry about the differentiation here. So now I try to choose delta sigma that satisfies additional condition that okay, delta sigma that produce delta B equal to 0. Okay, actually delta sigma here is arbitrary, so it can generate delta B equal to 0 or not equal to 0. Okay, but now I try to choose only delta sigma, okay, that produce delta B equal to 0, and also produce delta sigma ij equal to 0 on the boundary as well. Okay, is that clear to you?
Yes, Ajahn.
Okay. If I look at all admissible delta sigma, so let me draw a set. Let's say that this is a set. I have a set that contains all admissible delta sigma. Okay, so this is what I have. Delta sigma that sit in this set. We require to satisfy only two conditions. The first one, it have to be smooth enough. You can take derivative of that function. And the second one, when you take delta sigma and multiply by nj, you get 0. That's the only two conditions that you have to satisfy. Okay, so you can see that in this set contains infinite number of delta sigma. Some of them that sit in that set. Let's say that okay, I use a smaller circle here. Let's say that this set that I talk about here is delta sigma that also satisfy in addition the two conditions here. The first one is this and the second one is that. I just choose only the delta sigma that satisfy the condition that it's produce delta B equal to 0 at every point in the body. And also delta sigma is 0 on the boundary of the body. Okay. So delta sigma that satisfy two additional conditions here will be let's say that will sit in that set. Now we know that equation 1 is satisfied for any choice of delta sigma that sit in the big set here. So it have to be satisfied for any delta sigma that sit in a smaller set as well, right? Is that right? Okay. So now I try to restrict attention to a smaller set here. That delta sigma also satisfy the two conditions that I have here too. Okay. So now based on that choice, what will I get? If I look at this choice of delta sigma, you can see that the term here that I have is 0, right? Because I choose delta sigma that satisfy that condition. Okay, delta bi that generated by that delta sigma is 0, so that term disappears. Also, I choose delta sigma that is 0 on the boundary as well, so that term disappears. Because delta sigma is 0, so delta t will be 0 too on the surface SU. So that term disappears. So now equation 1 becomes this. Okay, is that clear? Okay, so now equation 1 reduced to equation 2, and that equation 2 is valid for any choice of delta sigma that sit in a smaller set here. Okay, and the smaller set that I have here is still infinite set. Okay, there are infinite number. There's infinite number of delta sigma that sit in that smaller set. So I can say that delta sigma is still arbitrary. Okay, you have many elements, infinitely many elements that sit in that set. Or I can say that this equation is still satisfied for many choice of delta sigma that sit in the smaller set. Okay, is that clear to you? Because delta sigma ij comma j is 0. Okay, I should, if you look at the delta sigma that sit in that set, delta sigma ij comma j is 0. Okay, for every point in the body. And also I have delta sigma ij equal to 0 on the boundary of the body too, right? Okay, so I can say that delta sigma that sit in that set satisfy some special property, and if you use the knowledge from vector calculus, now you can prove that, or you can show that there exists the symmetric second order tensor A, that the value and derivative of that second order tensor vanish along the entire boundary, and also satisfy the following condition. This part is quite difficult to prove here, but I think that if you learn vector calculus before, you saw the proof of this theorem before in your class, right? I am not sure that you remember or not. If you cannot remember, you can just simply go back and review the material that you learned before in vector calculus. But if you don't care much about the proof and you believe that the theory here is correct, now you can just simply trust what I have here. Okay, but if you want to know the background of the theorem, you can go back and review that material. Okay, so what I try to say here, whenever delta sigma that satisfy the two condition here, so when delta sigma satisfy that two condition, okay, there exists the second order tensor A that is symmetric, and the value and derivatives of A along the boundary is 0 and satisfy that equation. Okay, so this result from the theory in vector calculus. So now I can say that the sigma that satisfy the two conditions here, or the one that sit in a smaller set that I just mentioned, can be expressed in terms of the second order tensor A, like that. Or I can say that the sigma can be expressed in terms of the double curl. If you look at the expression here, this is the double curl of A, double curl of the second order tensor A. Okay, so once this one is satisfied, these two conditions are satisfied. So now you can always express delta sigma in terms of the double curl of A. Okay, and A here is a second order tensor that have the derivative and the value of A equal to 0 on the boundary, at every point on the boundary. Okay, now I can use this information. Okay, I can replace delta sigma that I have in equation 2, okay, by that one. What will I get? When I replace delta sigma ij by that one, I will get this. I will get this. So that equation have to be equal to, have to be satisfied for any second order tensor A that vanishes along the boundary, including the derivatives as well. Okay. So the volume integral here have to be 0. Now I can performing the integration by part of equation 4 here using divergence theorem again. Okay, you can go back and try to do that by yourself. Okay, I simply apply divergence theorem to integrate that one by part twice. I will get something like this. Okay, so that is the result from divergence theorem. Okay, after I perform the integration by part twice, okay, I will get this equation. Now, when you look at the term on the boundary, so we have two boundary term here, and the two boundary term here, the two boundary term here result directly from the integration by part twice. What happened to the boundary term? Because I told you that A here is a second order tensor that the derivative of A and also the function itself are 0 along the boundary. So what does it mean? That term is 0 because this is the boundary, right? And that is the boundary. So that term is 0 too. So that two term disappear then. Okay. Now I end up with equation 5. Okay. So the integral of that term have to be equal to 0. Okay. Now when you take a look at this A, because I told you that A here is arbitrary, because delta sigma is arbitrary. Okay. Delta sigma can be expressed in terms of A because delta sigma is arbitrary. Delta sigma that I talk about here is delta sigma that sits in a smaller set, but it still contains infinite number of elements. So delta sigma is still arbitrary. So that one is arbitrary too. Now you take the integral of the product between arbitrary function and that function, and the integral there is always 0. So what is the conclusion here? What is the conclusion here? Because A is arbitrary due to delta sigma that arbitrary. So now I can say that from 5, I can show that the term there have to be 0. That's the only way that possible, right? So if that one is non-zero, now I can choose that one equal to the one that is non-zero. So now the product there is positive. So the integral here cannot be 0. So that leads to the contradiction, right? So the only the only possibility that we can have here, that one have to be 0. That term have to be 0. If you remember, the one that I put here is simply what? This is a compatibility condition in terms of strain, right? Right? This is the double curl of epsilon ij. So that is simply the compatibility condition that I mentioned to you before, right? So now you can see that starting from Q, now we can prove that the compatibility condition is satisfied. Now I got one condition for P, right? Because P here that I have the compatible deformation. We need two conditions, right? So all I can say that the deformation is compatible imply two conditions. The first one, compatibility of strain have to be satisfied. And the second one, the displacement have to be consistent with the prescribed displacement on the boundary SU, right? Now I already proved the first one. So this is what I call the compatibility of strain. Okay. Now I confirm that starting from Q, now I can prove that epsilon is compatible, or strain is compatible. Is that clear to you? It still remains to prove the second condition, right? How can we prove that? Based on the first condition they got here, now I am sure that the displacement U exists, right? And satisfy that condition. Okay. Or what I try to say here, I can perform the integration of this equation or solve this differential equation. I can get U. Okay. So U exists. Or equation 6 here is valid for the displacement U, right? So now I can start from equation 6. And then I plug in equation 6 into equation 1. Now I get this. Is that clear? I plug in equation 1. If you go back to equation 1, you have epsilon ij, right? I write down epsilon ij in this way. I plug that thing in equation 1. You may have a question, why don't I try to plug this thing in at the beginning? Why I have to do this kind of proof before plugging in equation 6 into equation 1? Can anyone here tell me why I have to do a long proof here before I can use equation 6? Because you cannot start by plugging in equation 6 into equation 1, because you have to make sure that the displacement exists before you can use equation 6. You know what I mean, right? I cannot plug this thing in equation 1 directly without proving the existence of the displacement field. So what I prove here, I try to confirm that this equation is satisfied, or the strain is compatible, and then the displacement field exists. Once the displacement field exists, now this equation can be used. Okay, so then I plug in equation 6 into equation 1. Now I get this equation. Okay, I get equation 7 here. Is that clear to you? Okay. Now I can move on. Again, I can use the symmetry of delta sigma. So the first term on the left-hand side of equation 7 can be simplified because delta sigma here is symmetric, right? So now I can reduce this into the gradient of the displacement, right? So I will get equation 8, right? Like this, okay? So I just simply use the symmetry of delta sigma. Okay, that term can be reduced to this one. And then, again, I can perform differentiation. I can use the product rule of differentiation. So now I can write down the first term on the left hand side here. Okay, you can see that if I use the product rule, you can see that the one that we have here is similar to the one that I have in equation 8, the first term there. So I can replace that one by this one, subtract by that one, right? Okay. So then you get this one. You plug the thing in equation 8, and then you move term that the term that involving this one to the right hand side, then you can combine with that one, you get this term. Okay. And this term you just keep on the left hand side. So the final equation becomes this. Okay. I didn't do anything with that term, just keep it like that. Okay. Now, if you take a look at the first term on the left hand side, what is that one? What is this quantities? Again, if you look at that one carefully, this is simply a vector, right? With j as the free index. So now you can think about this vector vj. So we have again vj comma j. So that one is the divergence of a vector. Now you should think about divergence theorem. So now I can replace the integral here using divergence theorem. I can replace the volume integral here by the surface integral or the boundary integral. So what will I get? After applying the divergence theorem to the first term, I end up with this equation. Okay. Now, if you take a look at the first term here, that is what? If you look at that one, that is a virtual traction, right? Delta sigma ij nj is the virtual traction. And you know that delta sigma is admissible. So delta sigma ij nj will be 0 on that surface. Okay, so that term is 0 on that surface. Is that right? And now the integral over the entire boundary reduced to the integral over the surface SU. Is that right? Okay. So I use the condition that delta sigma ij nj is 0. Okay. Just a second. And we know that delta sigma ij comma j plus delta bi is 0 as well. So that term disappears, right? Is that right? So I think this one is wrong. Maybe this have to be replaced by delta ti. Okay, that is wrong. So why don't you just correct that to delta ti? So basically delta sigma ij nj equal to delta ti on the surface delta on the surface delta omega. And we know that, is that right? Maybe that is wrong. Sorry. Let me check this. So this one have to be 0 on, this should be st. Okay, so that equation is right. Okay, but the surface here have to be st because delta sigma is admissible. So this term and this term have to be 0 on the surface st. Okay, and we know that delta b, the virtual body force, have to satisfy that condition. So that term disappear then, right? So that integral disappear. So what should we get here? We're gonna get something like this. I reduce the integral over the boundary by I replace that by the integral over SU because delta sigma ij nj is 0 on the surface st, right? Okay, and that term disappears. So now I got equation 10. Okay. And we know that delta sigma is arbitrary, right? Is that right? Delta sigma is arbitrary. So delta Ti here will be arbitrary too. Because delta Ti that I define here, the virtual traction is simply this one, right? Okay, so if delta sigma is arbitrary, delta T here is arbitrary too. So now you can see that equation 10 is valid for arbitrary choice of delta T. Okay, resulting from the arbitrariness of delta sigma. So this equation is satisfied for that arbitrary choice if and only if ui here and ui0 have to be the same, right? On the surface SU. Is that right? You can see that this integral, we perform the integral on the same surface SU. And this one is the same, but it's arbitrary. So the two surface integral here can be identical if and only if, okay, ui and ui0 are identical for arbitrary choice of delta Ti. So this give us this result. So ui have to be equal to ui0 on the surface SU. And this end the proof. Now we got the second condition, right? We got the second condition to confirm that the deformation is compatible. Okay, so now we got P. By starting from Q, now we got P. Okay, so we done with the proof of the implication in the second direction. Do you have any question about anything here? Okay, let me make remarks here before I finish the lecture today. The principle of complementary virtual work allows you to replace the compatibility condition in the classical form and also the essential boundary condition. You can replace that by the virtual work, the complementary virtual work equations. Is that clear to you? So now instead of enforcing the strain compatibility condition directly and also the essential boundary condition, now you can use this equation instead, right? You can just simply use complementary virtual work equation. Okay, it will be better in some sense. Okay, when you try to solve the problem, and also the principle of complementary virtual work that I show you here is independent of material behavior. So even though the material is not linear, it's not elastic, the principle of complementary virtual work that I mentioned here still apply. Because in the proof, you can see that I don't have any assumption on the material behavior. Okay? But for linear elastic material, if the material that we focus on is linear elastic, what happened to the theory here? The complementary virtual work equation can now be expressed in terms of stress. Okay, by using stress-strain relationship. Okay, this is the principle complementary virtual work that expressed in terms of strain, right? You can see that we have strain here, but we can replace strain that we have in the left-hand side by stress using stress-strain relationship. We can always express strain in terms of stress using the Hooke law, right? So SIJKL here is the elastic compliance. So basically, this one is the inverse of CIJKL. Okay, so we can write down strain in terms of strain, and I can plug it in here. So now I end up with this equation. So this is simply the complementary virtual work equation expressed in terms of stress. Okay. This equation can be used later in the formulation. If you remember, when we try to formulate the problem in terms of stress, we have to enforce the compatibility in terms of stress. This theory, okay, the principal complementary virtual work allow you to replace the compatibility in terms of stress that I mentioned before in the formulation in lecture 1. You can replace that equation by this complementary virtual work equation in the formulation. Okay, I will show you here. So let's say that we look at this problem. If we want to formulate this problem by choosing stress as the key unknown. Before, if you remember, you have compatibility condition as the key governing equation, right? And also you need to have the essential boundary condition as well. The principal complementary virtual work allow you to replace the two here by the complementary virtual work equation. If you plan to formulate the problem in terms of stress tensor. So this is the final formulation. If you remember that I show you the third formulation in terms of stress, you can go back and then compare. So now we can just simply formulate the problem like this. We want to find stress field. The satisfy equilibrium. Now I replace the compatibility condition in terms of stress by what? Complementary virtual work equation. The principal complementary virtual work equation allow me to replace that by this one. And also the boundary condition that we used to have two boundary conditions, right? We have the essential boundary condition on the surface SU. And we have the natural boundary condition on the surface ST. One of them can be removed because that is included in this equation already. Okay? You can go back and compare the one that we got here and the one that we have before. So we just simply replace the compatibility condition and essential boundary condition by this equation. Okay, we can do in this way because of the principle of complementary virtual work. Okay, so I will stop here for today. Okay, do you have any question about anything? Now I prove two important theorems for you, right? The first pair, the principal virtual work and the principal complementary virtual work. The pair that I proved for you here is very crucial. You can apply the two principles here to do several things. Okay, at least, okay, you can take a look at the techniques that you learn from structural analysis class. You apply both of them here. For example, the principal virtual work you can apply in the derivation of stiffness approach. And the principal complementary virtual work here you can apply when you try to derive the flexibility approach. Okay, so the two theorems here are very important. So I hope that okay, the proof that I show you here will provide you the background and you know basic information. Okay, now you know, okay, how can we get the principle? How can we prove them? Okay. Next time I will talk about the remaining theorems, but I will not prove it again. Okay, because the remaining theorems that I will mention in this class can be proved using the first two theorems that I just proved here. Okay. Do you have any question about anything? มีคำถามอะไรไหมครับ I also post the second assignment